In the last video, we saw the idealized versions of gasoline and diesel engines. Today we will see the idealized version of jet engines. These are called gas turbine engines. The idealized cycle representing gas turbine engines is called the Brayton cycle. Gas turbine engines usually operate on an open cycle, which consists of air being drawn into the compressor from the atmosphere, where the temperature and pressure are increased. This is then mixed with fuel and burned in the combustor at a roughly constant pressure. This further increases the temperature of the gas, which then enters a turbine, where energy is extracted as the gas expands back to atmospheric pressure. Just as was done in the previous video, this can be approximated as a closed cycle, as the air is returned to its original state at the end of the cycle. Therefore, the combustion can be modeled by a constant pressure heat addition process, while the exhaust is approximated by a constant pressure heat rejection process. The Brayton cycle is composed of the following four internally reversible processes. From 1 to 2, we have isentropic compression, which occurs in the compressor. From 2 to 3, constant pressure heat addition in the combustion chamber. 3 to 4, isentropic expansion in the turbine. And then from 4 to 1, constant pressure heat rejection. This last step occurs through the nozzle and diffuser. All four steps in this idealized process occur under steady flow conditions. To begin the analysis of the efficiency of the Brayton cycle, we can start with the usual definition for efficiency. A to B equals 1 minus Q out over Q in. In this case, Q in is equal to Cp times T3 minus T2, and Q out equals Cp times T4 minus T1 due to these constant pressure processes. So A to B equals T4 minus T1 over T3 minus T2. Then, similar to the analysis in the previous video, from 1 to 2 and from 3 to 4, we have isentropic processes. So T2 over T1 is P2 over P1 to the K minus 1 over K power. And then the pressures P2 and P3 are the same. Pressures P1 and P4 are the same. So that equals P3 over P4 to the K minus 1 over K power. And then again, because this is isentropic, that equals T3 over T4. Again, taking out T1 from the numerator and T2 from the denominator, we're left with this expression where these terms in parentheses are going to cancel, and we are left with 1 minus T1 over T2, which is the same as 1 minus P1 over P2 to the K minus 1 over K power using the isentropic relationships. And then we can define Rp to be P2 over P1 as the pressure ratio. So the efficiency of the Brayton cycle is A to B equals 1 minus 1 over Rp to the K minus 1 over K power. Note that this pressure ratio is the pressure ratio through the compressor. Similar to what we saw in the last video, the efficiency of the Brayton cycle increases with both pressure ratio, Rp, and specific heat ratio, K. Typical pressure ratios for compressors are in the 5 to 20 range, as seen down here. This leads to typical efficiencies of 35 to 60% for the Brayton cycle. One limitation of jet engines comes in the form of the combustion chamber. With the high pressure air coming in after the compressor, it is possible to achieve very high temperature air after the combustion process at state 3. So high, in fact, that the material used to build the combustion chamber must be chosen carefully so that it can actually withstand these temperatures of over 1,000 degrees. This in turn actually limits how high the pressure ratio can be. The net work output increases with pressure ratio at smaller pressure ratios, but then reaches a maximum and then actually begins to decrease as the pressure ratio increases. It can be shown that this maximum work output occurs at a pressure ratio of Rp equals T3 over T1 to the power K over 2 times K minus 1. The compressor requires work in to compress the air. This work comes from the turbine. They're usually connected by a shaft, as seen back here. The ratio of the work taken by the compressor to the overall work produced by the turbine is called the back work, denoted RBW, where RBW equals WC in over WT out, or work coming into the compressor, divided by work output by the turbine. This value is usually pretty high. More than half of the power produced by the turbine usually goes to drive the compressor. The Brayton cycle, like the Carnot cycle, will never be achievable in real life. There will always be pressure drops in the heat addition and rejection processes, and loss of energy due to irreversibilities. Therefore, the ideal, achievable gas turbine cycle differs from the Brayton cycle due to these. This leads to isentropic efficiencies for the turbine and compressor. For the compressor, A to C equals WS over WA, the isentropic work in over the actual work in, which can be approximated by the enthalpies between states 1 and 2. For the turbine, A to T equals WA over WS, the actual work out over the isentropic work out, which again can be approximated by the enthalpies between states 3 and 4. Some notes about gas turbine engines. The air is used as both an oxidant for the combustion as well as a coolant. For this reason, there is usually a very large air-to-fuel ratio, above 50 to 100. So the air standard assumptions are applicable here. This also means that the mass flow rate through the turbine is slightly higher than that through the compressor. Usually this is small enough that it can be ignored. By only having air as a working fluid, this actually means that we are underestimating the performance of the gas turbine engine. So this is a more conservative estimate, which is generally the way you want to go in engineering. The thermal efficiencies of real gas turbine engines are usually around 25 to 45%. The higher values occur when there are improvements to the standard Brayton cycle, such as regeneration and intercooling, which we may see in the next video. That brings us to the end of the analysis for gas turbine engines, which also brings us to the pre-lecture example for this video. I will see you all in class and answer any questions you may have at that point.